Hello, good morning. My name is Chong Ho Yu, also known as Alex. You can call me Alex Yu or Hey You. In Christmas, you can call me Ho Ho Ho. So my talk today is based on my book, Data Mining and Exploration. You can buy the book from Amazon.com. If you like my talk, you enjoy my presentation, please support me and buy my book. So today I'm going to talk about the transition, the connection from the traditional approach to the modern approach, data science and machine learning. So let's start from a story. Just imagine this person, Carl Fisher, back in 1981, he earned his PhD in statistics. Then he found a faculty position in a well-known university. And he applied what he learned in teaching and research. His course covered all essential concepts and procedures in the field, such as t-test, ANOVA, Pearson coefficient, least square regression, chi-square analysis, multivariate procedure, factor analysis, even structural equation modeling, blah, 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 and so on. So everything was fine. Suddenly, his whole world turned upside down. In 1993, he was run by a truck. Then, he fell into a deep coma for 3 decades. In 2023, this year, suddenly he woke up and he recovered. Not only did he recover, but also he recovered his mental ability, his intelligence, his skill are all intact. Well, so he tried to restore his life, but he worried that he could not find a job because, as mentioned just now, he fell into a deep coma for 3 decades, and now there exists a 3-decade knowledge gap. So he tried to catch up, and he started applying for job, and then he picked up some textbook and tried to catch up, try to stay current. But after reviewing several syllabi and textbook, he felt much better. Wow, what a relief, relax. Why? He found that most textbook he reviewed covered the same content as 3 decades ago. T-test, ANOVA, Pearson coefficient, least square regression, chi-square analysis, or more like ANCOVA, ANOVA repeated measure, and so on. Or you may see something like stepwise regression, logistic regression, but basically the basic framework remains unchanged for a few decades. Okay, so why do I tell you this story? Well, the story, actually I make up this story. It's not a true story. However, it's also a true story in some sense. You could just fall asleep for several decades and then wake up and then find that, okay, everything remains more or less the same. However, should we do that? Should we recycle the same old? Or should we step outside our comfort zone, look around the world, stay current? I always tell my students, even if you cannot change the world, but you should change with the world. So, we have to be aware what's happening in the world, especially in industry. Today, when you wake up, when you open any news channel, when you open a website related to data analysis, you may see all this jargon, right? ChatGPT, Google bar, AI, machine learning, deep learning, data mining, data science, and so on. So, should we isolate from this trend, or should we really think about how to make the transition from the traditional approach to a more modern approach? Let's face it, what we have been doing is quite old. For example, regression analysis. Okay, the principle is the least square criterion. The least square criterion was discovered in 1805, when my great-grandfather was born. Okay, Pearson coefficient was discovered in 1892. By whom? By Carl Pearson, of course, right? How about chi-square analysis? In 1900, the turn of the century, okay, also by Carl Pearson, but later Fisher add the concept of degree of freedom, okay, to make it better. How about t-test? 1908. ANOVA, well, ANOVA around 1930s. Randomization, experiment, and so on. So this is the gold standard created by R.A. Fisher. Okay. Well, are there anything better, more powerful since 1930? Since World War II? Yes, of course. Yeah. For example, CNN. Not that CNN, not the news channel. CNN is convolutional neural network. Actually, the prototype of neural network was made back in 1950, okay, by psychologists. But the mature CNN that was put into production appeared around 1980s. Okay. And decision tree, 1984. C4.5 algorithm, enhancement of the original decision tree, was created in 1993. Boosting, 1997. Random forest, 2001. Also elastic net, 2005. Adaptive lasso, 2006. XGBoot, 2014. And there are more happened after 2014. What you see is just a few examples. However, when you look at the textbook today, well, so you hardly come across these terms. What's happening? Well, in my experience, most people, they would like to stay with what has been working for them. Okay, what's that? Well, using the p-value to reject the null, not to reject the null, to test a specific hypothesis, to confirm or disconfirm a theory. This has been the norm for about a century. As you may already know, this practice has been challenged by so many researchers. Back in 1989, Professor Kenneth Brockman, he started a journal. So he started a journal by trying to introduce a new approach, a new idea. So he told people, when you submit your paper, try to do something else. Do not over-rely on p-values. However, the Earth is round. When he left his position in 2001, then the journal just returned to the good old p-value tradition. Okay. So, somebody may ask, well, okay, p-value has been working so well. What is the problem? Okay. The problem is, well, the logic isn't quite right. As a philosopher, I can tell that, well, it may commit some kind of logical fallacy. How so? Why? Well, first, the approach starts with this logic. Given the hypothesis, what is the chance of observing the test statistic from the data in the long run as expressed by the sampling distribution? So the form is a PDH. Given the hypothesis, what is the chance of observing the data, right? However, what we really want to know is opposite. We want to know, given the data, what is the best theory to explain the data, no matter whether the event can be repeated. We care about the data at hand, the data pattern. So it should be PhD, given the data. What is the best theory? Okay, or which one is more likely to be the best explanation? Inference to the best explanation. Okay. As mentioned just now, well, the logic isn't quite right. I would say there exists some kind of logical fallacy. What's that? Affirming the consequent. Okay. PDH is not the same as PhD. So, if H then D does not imply if D then H. It's okay to say that if H then D, H therefore D. But you cannot say, well, if H then D, now I see D, it must be H, or D support H. It's not the way to go. Well, now researchers, they follow this logic. Oh, I introduce a new treatment, a new model. If my treatment is working, if my theory is correct, then I should observe such and such data. So, if my innovative treatment is working, then my students should improve their performance. Oh, performance is improving. Test score is rising. Yeah, my treatment is working. My theory is correct. Yeah, wait a minute. Not yet. Why so? Well, consider this situation. If George Washington was assassinated, then he's dead. Now he's dead. Okay. Therefore, he must be assassinated. You know history. You know US history. You know it's not true, right? Now let's use another example. If it rains, the ground is wet. The ground is wet. It must rain. Well, okay. You may argue that if it rains, the ground is wet. Now it's raining. Therefore, the ground must be wet. If A then B, A therefore B. Okay. But you cannot reverse it. You cannot say if A then B, now B, it must be A. The ground is wet. There are other possible explanations. Flooding, or the pipe is leaking, and so on, right? There are other competing alternate explanations. Okay. Another problem is, well, when we over-rely on the p-value, when we follow the so-called p-tradition, funny thing may happen. This one is really, really funny. I cite it in my class and people laugh. Okay, so when I was a student, my professor, Dr. Larry Tufeter, he told me that, well, when you have a large enough sample size, virtually you can prove anything. When you keep increasing your sample size, you will be always right. Really? Okay, let's look at this study at Cornell by Professor Bang. Okay, So Professor Ben, he conducted some experiment to assert that ESP is real. ESP stands for extrasensory perception. Okay. Look at his sample size, 1,000. Well, by today's standard, it's nothing, right? Yeah, but so today in Amazon, Google, Microsoft, every day you can access a sample size counting in 1,000, 100,000 or million of observations. However, still, when you have a few hundred or a few thousand, it is very easy to reject the no, to confirm your so-called theory. So what is his theory or his experimental configuration? Well, in one study, there were two curtains. Behind two curtains, one of them posed a nude female picture. Okay, so the participant, the male human subject were asked to tell behind which curtain there will be a nude woman picture. Okay. Well, only two curtains, right? The chance that you can be right is 50%, right? Yeah. In his experiment, the actual hit rate is 53.1%. Okay, 3.1% better is a big deal. By common sense, you know that not a big deal, right? It's not too far away from 50%. But when you have big enough sample size and you keep, do the p-hacking, then, reject the no, ESP is real. And guess what? The paper was published. Well, so you may argue that, nobody trusts this result. Nobody will believe that ESP is real. However, do you know that there are so many findings or false findings affecting our decision, our action? Okay. For example, in this study about the effect of aspirin. Well, so based on this study, doctor recommend that taking aspirin can reduce the risk of heart disease and so on. Okay. However, look at the sample size, 22,000. Well, the p-value is less than 0.0001. Yeah. Okay. However, the effect size is only 0.77%. Well, so future research found even smaller effect size. Now, people modify the recommendation. If you are healthy, then no need to take aspirin. But if you had heart disease before, it may be advisable to take it. Okay. As you may expect, when we over-rely on the p-value, so when you get big enough sample size, when you continue doing p-hacking, you can get something. You can get something to report. Back in 2015, OSC found that a large number of studies published in high impact factor journal cannot be replicated. Most of them, 97% of those studies report significant p-value, but in replication, only 36% of those studies can yield significant findings, and the effect size is much smaller than the original study report. Okay. This crisis, so-called the reproducibility crisis, also known as the crisis of replication, draw the attention of ASA. Okay. Now the question is, well, should we do something better? Okay. How can we affirm the conclusion when we are unable to recreate the same finding in other situations, other settings? Okay. Also, in traditional statistics, well, remember we obtain the test statistic and then we compare the test statistic from the sample against some sampling distribution, right? Okay, so we assume we know what the distribution should be. The problem is when you do that, in some sense, you are not making the inference from the sample to the population. Rather, you try to infer from the population to the sample. Your assumption about the population dictate how you deal with your sample. John Tukey, the father of EDA, questions are reliant on so-called known distribution. He asserts that progress of statistics or progress of data analysis can only be made when we move away from pretending to know the distribution, pretending, your data structure can meet the assumptions. Okay, the next thing is about estimation. Okay, for a long time, people have been using so-called the point estimate, but now, okay, according to APA, well, besides the p-value, also report the interval estimate. The problem is even if the researchers report the interval estimate, however, that is not a chance statement. CI is not probabilistic. It's not. Okay, so you are not saying that 95% chance the population will fall within the interval. It's not the point. Well, actually, no matter you use point estimate or interval estimate, the population parameter is assumed to be fixed. It's a fixed constant. In the population, there exists only one single true parameter, one single true number, one single version of reality. However, when you sit back and think about that, this is problematic. This is unrealistic. Why so? The population is not a closed system, right? As I am talking, there will be new members joining the population. Also, some people will leave the population. People or observation or event popping in, popping out, right? Yeah. Every single day, single hour, single minute, there will be new observation, new event, and so on. It's an open system. So, the population, the parameter, is a moving target. As you may know, Bayesian do not buy that. Bayesian reject the notion of a true fixed constant in the population. Okay. So, what shall we do? What should we do? Well, the next problem, is well known, right? 0.05, 0.05. Well, when you get a 0.06 or 0.051, 0.052, oh, you could not sleep, you could not publish. Oh no, the end of the world. Well, actually, when Fisher introduced the cutoff, he had no intention to make it fixed. Rather, we should make the judgment on a case-by-case basis. Somebody say, well, God loved the 0.06 nearly as much as 0.05, right? 0.052, 0.055, what a big deal, right? So, but all this problem could be overcome in modern data science and machine learning. Why? You'll see why. Okay, so the problem is the cutoff lead to mechanistic conclusion. Your conclusion is dichotomized. Yes or no, let me go, right? Somebody argued that, well, even Bayesian, okay, even if you use something else, the Bayesian approach, machine learning, but eventually you have to make a decision. You have to accept or not to accept the theory. You have to implement the policy or not. Well, the problem is not only the decision is dichotomized, but also the evidence is dichotomized. 0.5 or not. Okay. Now we have entered the era of big data. You know that t-test, ANOVA, chi-square, and so on, all made in late 19th century or early 20th century or mid 20th centuries. Okay, well, they were made for small sample study. When you apply this to big data, it becomes irrelevant. It becomes misleading. Okay, so let's look at this study. Well, these researchers access Facebook data, 61 million observation. Okay, social media data. I will not talk about, their theory, what they want to test. Okay, it's not the point. It's irrelevant. The point is the sample size, 61 million observation. And guess what? They conduct a t-test using 61 million observation. They report the p-value. And guess what? The paper was accepted and published. However, somebody laughed at it. Well, in a now famous experiment on social influence on voting carried out on Facebook, a data set that was millions of likes, 61 million observation, was analyzed with the 100-year-old t-test, which had been created to deal with a problem of small sample size. You do not want to be famous in this way, right? People use your research study as a counter example. You don't want that. Okay. So, guess what? You may think, oh, people learn, right? People learn from the mistake. Well, in 2014, some people made the same mistake. Another researcher at Cornell once again used Facebook data. Although this one isn't as big as the last one, the sample size is 689,000, but still a large number. Okay, so the study is about how information being fed to the social media user could change their perception, their behavior. So p-value, p-value less than 0.001, p-value 0.007, blah blah blah. Oh yeah, okay. So the conclusion is that the information that you feed into social media can affect people perception and behavior. And the study was a big hit. More than 330 news outlets report this finding. Well, this is highly problematic. Well, okay, so the bottom line is, what shall we do? Well, I do not suggest totally do away with traditional statistics, However, we do need different tool sets. So we need the tradition and the modern, the old and the new in parallel. The world is changing. The only constant is a change. What do we want ourselves to be? To be like Kodak, Blockbuster, and Sears, or want to be like Sony, Netflix, and Amazon? Keep reinventing ourselves. Okay, so what is the difference? Well, between the old and the new, the algorithm, the machine learning algorithm, the data mining algorithm created in the late 20th century and early 21st century are more efficient, more powerful. Okay. For example, AI algorithm used by YouTube, Netflix, Amazon, Google, and so on can process trillions of observations in a second, and the result is highly accurate. Even though using a laptop with only 16 gigabit of RAM, you can complete the entire analysis in half an hour, even though the sample size count in millions. However, when you use traditional method, it will take like days or weeks. You need a supercomputer. Okay. And also SageMaker. SageMaker is made by Amazon. SageMaker is utilized to detect online fraud. Even though the data size is gigantic, the prediction time is cut down to about half an hour, and the cost is less than $10 a month. Moreover, the predictive accuracy improved 25%. So, the good thing is that you don't need a supercomputer to run the program. What it takes is an 8-core CPU and 2 gig of RAM. Okay, more efficient. Okay, today you may come across this buzzword, this jargon, data science, data mining, big data analytics, AI, machine learning, deep learning, and BI, and so on. I will not explain every single one, so I will briefly show you the basic definition. Okay, so DS is a fusion of data analysis, computing, and domain knowledge. Data mining, analyze structured data. So you may say it's a subset or a specific application of DS. DS incorporates both data mining and text mining. Text mining is for unstructured data. And today AI, machine learning need big data because for ongoing improvement, you need to continue to feed big data. So the idea is something like resampling. Okay, BI is a specific application of data mining in business setting. Okay. Somebody can say, well, DS consists of 4A: architecture, how you design a system to store, to manage your data; data acquisition, how you collect data; data analysis, machine learning, pattern recognition; data archiving, make the data reusable. So to make big data happen, you should not destroy your data, just let it accumulate. Okay, you may see this graph quite often. So DS is, you may say, is the intersection between data analytics, computing, and domain knowledge. Okay, so we will focus on computing. In traditional statistics, well, usually we learn the test procedure. We don't talk about like the data warehousing, data mesh, data architecture, right? Because there's no need. You can put everything into Excel. So the The problem is when you have small data, then the procedure cannot learn. The procedure can yield a result specific to a particular sample, so-called overfitting. But however, today, big data, AI, machine learning, they are all adaptive. They can learn from the data and will get better and better. For this reason, Google predicts that China may overtake the US in machine learning because China produces more data than us. Okay. And also in the past, as mentioned just now, you learn the test procedure, you don't learn how to configure a server, cloud computing, data mesh, and so on, right? Yeah, but today, when you have big data, then you need to learn like SQL, also Oracle, and so on. How to structure your data, make it accessible, easy to manage, and ready for analysis. Also in the past, data are isolated. Yeah, so when researchers are done, they put aside the data, and then later they destroy the data to protect the human subject, but not in corporation. So now they keep the data, and the size is getting bigger and bigger, so that you have big data to feed into the machine learning algorithm. Okay, so today, we have big data in terms of high volume, okay, high dimension, big sample size, also real-time data. Okay, so you keep updating the data to fine-tune the model. The machine can learn with incoming data. Also, not only data in numbers, but also the machine can learn from text, learn from audio, learn from video, learn from all kinds of unstructured data. Okay, what are the common ground of all of this? Data science, data mining, big data analytics, machine learning, deep learning, BI. Well, number one, unlike traditional statistics, it's data-driven, not model-driven. You care about the data at hand, not about the long-run sampling distribution, okay, or the unknown population. Number two, it's about pattern recognition, not using a single cut-off point, 0.05. Number three, rather than feed all your data into a single model, one shot, you run a multiple model, support vector machine, random forest, and so on. Then you perform ensemble method, model comparison. Number four, use AI rather than only human judgment. Okay. So now we will spend a few minutes to talk about why big data. Well, not only modern algorithms are more efficient, but also modern data nature. The nature of modern data are totally different. Well, not totally, vastly different. For a long time, we count on what people told us, right? What the human subject tell us. The problem is people may not do what they say, may not say what they do, right? However, today, Google, Facebook, Amazon, you name it, collect behavioral data in a naturalistic setting. They record what people are doing or have been doing, not what they say. The problem is when people report what they say, they may lie or faulty memory. For example, so according to a survey, about 40% of people here attend church on a regular basis. But when researchers look at the actual record, actual attendance record, well, is only 22%. Okay, so this is a very famous example, right? The poll predict that Clinton will win in 2016, but turnout is opposite. Why? People do not do what they say, do not say what they do. So, this researcher used Google data, and then he overturned so many traditional psychological theory. People will appear to be nice to you when you are watching, but when nobody is watching, then people will say something else in Google. Okay, so Google data can tell more about human nature than traditional psychological data analysis. Okay, so I know it's almost a time's up. Okay, I will wrap up my talk. So, in the past, we reject the no, reject not to reject. But today, we use a pattern recognition. AIC, BIC, this number have no cutoff. Rather, you have model comparison. Okay, then you pick the model with the smaller AIC, BIC. Okay, and also second, no longer test a predetermined hypothesis. Rather, you are allowed to explore. Like John Tukey EDA, you may have like 100 or 1,000 potential predictors, and then you let machine learning AI find the pattern, propose a theory, inference to the best explanation. So, in the past, you may use a single method, but today, the norm is triangulation. You apply multiple modeling techniques, and then you centralize all findings in a hub, and then you perform model comparison, or model averaging, and also, in the past, you use all observation in one single analysis. The problem is, you may get overfitted result, overfitting. The result is good for one particular sample, but when you move to another setting, you cannot replicate. However, today we have, usually we have big data, and then you apply algorithm to partition the data into subset, and then you repeat the same analysis across all subsets. In the process, you boot the model, you fine-tune the model to avoid overfitting. So, once again, the traditional approach is good for small sample study, but today all the modern algorithms, they are built for big data, and also not only structured data, not only number, but also unstructured data. So, however, as mentioned just now, I don't mean from this point on we can do away with all the textbook, we can forget about t-test, ANOVA, linear regression. Actually, they could coexist side by side. And indeed, all the modern methods are built on the foundation of the traditional method. There are some common ground. For example, lasso, ridge regression, in penalized regression. They are built on the framework of regression, the traditional regression. When you run decision tree, you may use the log-worth criterion to determine how to partition the tree. Actually, log-worth is based on the p-value. Random forest is a form of resampling, bootstrapping. CV is a concept of resampling. Cluster analysis, PCA, they are all inherent from the traditional multivariate statistical analysis. The bottom line is they are not totally contradictory. there could be a natural and logical transition. And also, in some situation, you have to turn to traditional approach. For example, DS focus on prediction, but in traditional statistics, the focus is on inference and explanation. So when you want to, to make a causal inference, you may not need big data. Rather, you need right data. I'm not the one to say it. Pearl, a professor in UCLA, say that you need the right data, not big data. Data are dumb. You are smarter than the data, especially in causal inference. Okay. So the last is that not all research problems need powerful tools. When you have a small sample size, when you have 4 or 5 predictor, 3 to 4 predictor, using neural network is overkill. You may simply use something traditional. And also when you have hierarchical data, nest data, then you may turn to mixed modeling, multi-level modeling, hierarchical linear modeling. Is preferable, than doing neural network. Okay, so thank you very much. Thank you so much for your attention.